Hi, everybody. I hope our study of systems of equations has been going well. I'm reminded now of, I don't know if you've heard of Monty Python. Actually, it was even a little bit before my time, slightly. But he had this show, and there was this phrase they would always say that would go something like this. And now for something completely different. And that's how this is about to feel. We've been studying systems of equations here. And we're going to, I guess, see the application in this specific mathematical context. But keep in mind, this is pre-calculus. And so what we study is governed very much by what you will need in order to gain a deep understanding of the subject of calculus. So this topic had to go somewhere. We're putting it here. It's called partial fractions. And you will see, as we solve them, systems of linear equations embedded within them. But just know that this is typically a topic that comes back in a second semester calculus course. So you will see it again, but it probably won't be for a little bit, as you've got a couple classes before that. But you might make a note and be able to come back and revisit this later. So let's get started. All right, guys, so partial fractions. And like I said, this is something that we got to put somewhere. We're placing it here, and it will become hugely relevant in your future calculus studies. So what do I mean? Well, writing a rational expression as a sum or difference of rational expressions, each of whose denominators are prime factors of the original denominator, is called partial fraction decomposition. Think about it this way. Let's go back to yesteryear. You're sitting in, I don't know, some grade school class, and you're asked to add these two fractions together. And so you say, okay, well, my common denominator is 12. And so 2/3 is going to become 8/12. 1/4 is going to become 3/12. And so you get 11/12. And with that, now have more mathematical competence than 85% of all Americans. Congratulations. I'm sorry, did I just go off on a brief diatribe? I apologize for that. Partial fractions essentially says this. Suppose we have 11/12. And we want to write that, well, as a sum. Okay, and the question then is, what goes in each of these numerators? Okay, and so that's the game that we're going to play here. All right, what goes in each of these numerators? And so obviously for us, these will be rational expressions, so there'll be polynomials involved, but the spirit of it is just that. We used to go this direction, now we're going that direction. All right, so here's our first case. When you factor the denominator, the factors are all linear and none of them repeat. If that's the case, then here is the partial fraction decomposition. These A's, capital A's, these are all constants. And it should make sense, right? Because think about a reduced rational expression, if you will. The degree of the numerator needs to be less than the degree of the denominator. Otherwise, you can divide and then have a quotient with some remainder. Well, if these are linear factors, they're all degree 1. So my numerators need to be degree 0, which means constants, okay? Now there's a lot of notation here to get lost in, but let's make sense of it. And then after we do this next example, maybe go back and look at this definition here and find the pieces that we've discussed. So here we have partial fraction decomposition of 2x minus 3 over x squared minus 5x plus 14. And so the first thing I want to do is factor, right? I need to factor my denominator. And so when I do that, I'm going to get, well, x Oh, I'm sorry, guys. This was supposed to be a minus 14. Sorry about that. Minus 14. So I get an x minus 7 and an x plus 2. And so what we're doing is we are saying, okay, let's rewrite this as a sum. I'll use A and B. Okay. And now if you were to actually start on the right-hand side of this equation and combine, right, if you were to add the fractions, well, you would need to get a common denominator. And so that common denominator, we know, is the product. And so A would have to get multiplied by x plus 2. B would get multiplied by x minus 7. Okay. Now, what this tells me is that 2x minus 3 equals A times x plus 2 plus B times x minus 7, which is AX plus 2A plus BX minus 7B. And what I'm going to do now is gather the x terms and factor, and then my constants, okay? Now, remember, the left side of this equation is 2x minus 3. So what I'm going to do is equate coefficients. So the coefficient of x on the left is 2. The coefficient of x on the right is a plus b. So I have a plus b equals 2. While my constant on the left is negative 3, my constant on the right is 2a minus 7b. So here's my system of equations. So I'm going to multiply the top equation by 7. And when I do that, I'll have 9a equals 11. So a is 11/9. B, I know that a plus b is 2. So 11/9 plus b is 2. So b must be 7/9. Okay. And so there's my decomposition. I can write this, right? I'm going to come up here, and this a is 11/9, and this b is 7/9. Okay? All right. What if there are repeated linear factors? Excuse me. So here we still have constants in our numerator, but notice my denominators, right, are each raised to all the previous powers up to whatever multiplicity that factor has. Again, let's put it into practice. So we have 5x plus 1 over, well, x squared minus 6x plus 9 factors as x minus 3 quantity squared. So I'm going to have a over x minus 3, and I'm going to have b over x minus 3 quantity squared. If my denominator factored as x minus 3 quantity cubed. Then I'd have a third term out here. But now we play the same game, right? I'm going to equate the numerators after I get a common denominator. So A is going to need to get multiplied by x minus 3, and B already has that common denominator, right? It's x minus 3 squared. And so I can equate that to 5x plus 1. Again, remember my denominators now are really this. So I can equate my numerators. 5x plus 1 equals ax minus 3a, and then plus b. So equating coefficients, coefficient of x on the left is 5. Coefficient of x on the left is just a, so I know that a is equal to 5. And then I also know that negative 3a plus b is equal to 1. And so b will be what? Well, be 16. Okay. And so I have a, I have b, and so I can write the partial fraction decomposition. 5 over x minus 3 plus 16 over x minus 3 squared. Okay? All right. Well, what if there is a prime quadratic factor? Okay, so a quadratic factor that can't be, I'm sorry, a quadratic, okay, let me say this again. When you factor the denominator, there is a factor that is quadratic, and that quadratic factor cannot be factored any further. Well, then again, keeping in that spirit of numerator being less degree than denominator, if my denominator is degree 2, my numerator needs to be degree 1. Hence that form ax plus b, or a, in this case, ax plus b. There it is. It looks linear, right? So let's see how this plays out. And I've actually combined a couple things in this one because I want you to notice something, right? You could have any combination of these. So I'm going to factor this denominator, x squared plus x plus 11. And then what we have will be something over x. And notice x is to the first power. That factor of x is to the first power, so my numerator must be a constant. And then x squared plus 11x plus, I'm sorry, x squared plus x plus 11, that's not going to factor. And so this numerator is going to be bx plus c, okay? And so now we just do what we did before. I'm going to take 2x plus 5 over x times x squared plus x plus 11, and I'm going to get a common denominator. So my common denominator, right, is the product. And so a will get multiplied by x squared plus x plus 11. And bx plus c will get multiplied by x. Okay. And so now I equate 2x plus 5. I'm going to distribute this ax squared plus ax plus 11a plus bx squared plus cx. Okay. And then we're going to group and factor. So x squareds, factor out x squared, have a plus b. And then my x terms, ax and cx. And then my constant is 11a. Okay. Now I want you to notice, you might be saying, hey, wait a second, there's 3 terms on the right, but 2 on the left. Well, let's think about this. True, the left doesn't have a quadratic term, so I could think of it as 0x squared. And so now I get this set of equations. A plus B equals 0. A plus C equals what? Well, what's the coefficient of x on the left? It's 2. And then 11a equals 5. Okay, so this is a system of linear equations. Now, if 11a equals 5, then I know that a is 5/11. If a plus b is equal to 0, then b is negative a, which means b is negative 5/11. And then we have a plus c equals 2. So 5/11 plus c equals 2. And so c is going to be, well, 2 minus 5/11. 2 is 22/11. 22 minus 5 is what, 17? Okay. And so my partial fraction decomposition will look like the following. And then negative 5/11 plus 17/11 all over x squared plus x plus 11. And really, it might be worth noting that, you know, you can rewrite this as 5/11x, and then minus, and since these denominators are both 11, 5x minus 17 all over 11 times x squared plus x plus 11. Okay, if you're studying from a textbook or something and you get to the back and check your answers and the answer looks like this, but you've got that expression, that doesn't mean it's time to throw your book and say, I don't get it, right? It could just be that it's in a different but equivalent form. And honestly, that form that I left it in at the end it just kind of reads better, right? So don't just get to, you know, don't assume you've done something wrong. Okay, in fact, just as a general rule here, I would encourage you. You guys have come a long way in your mathematical studies, and a lot of times students have a especially in mathematics, right, where we're trained that we're supposed to go through a set of procedures that you've just observed your instructor do. And so just copy those steps, get the right answer. Well, you guys are getting much beyond that. And frankly, that's really shortchanging students on just what mathematics is. So I would encourage you, instead of immediately, if you see a variance in your answer between something else, instead of immediately saying, what did I do wrong? Ask what it means, okay? If I left this partial fraction decomposition unsimplified, that doesn't mean I did something wrong. It means I didn't simplify. There's a difference, okay? And so let yourself, you know, you've earned the opportunity to pause and reflect on the meaning of your work, what it's telling you, as opposed to just automatically dismissing it as being wrong, okay? All right, guys. So that's partial fraction decomposition. Again, you're gonna see it in a second semester or quarter calculus class. It's going to come up in what are known as integration techniques. Make some things that are complicated actually quite simple. But it only will be simple in your Calc 2 courses if you know how to decompose into partial fractions like we've just done. So, you know, I like to try to give a heads up where these topics will occur in your future. This is still a ways down the road, so you know, hopefully you're making notes of where these topics are, so you can go back and revisit when the time comes. I don't necessarily expect you to sit and review partial fractions from here until when you're sitting in a Calc 2 course. So there it is. Enjoy, work some problems, and as always, I wish you the happiest of studies. Bye-bye.